Hey everybody! Today we're learning to count using factorials, permutations, and combinations. All of these things rest on the fundamental counting principle, which says that if you have two events, and the first one can occur in m ways, and the second can occur in n ways, then the total number of ways the two things can happen is m times n, so you just multiply the number of ways. For instance, suppose we have a restaurant that offers 4 soups and 3 salads. There are 4 times 3, or 12, possible soup and salad combinations. A lot of times we illustrate the fundamental counting principle in particular examples with tree diagrams like this one. So you start at the top and you pick your soup. There's 4 different ways of doing that, so there's 4 different branches coming off of that top point. And then regardless of which one you choose, you have 3 possible salad choices. So here you can visually see 4 groups of 3, 4 times 3, 12 possible soup and salad combinations. An important warning here is that the fundamental counting principle only applies when the number of ways the second event can occur is independent from the outcome of the first event. So, as sort of a counterexample, suppose that at this restaurant we have a customer that only likes one of those salads when it goes with a particular soup. So there's no longer 12 possible soup and salad combinations for this customer. Instead, there are 10 because we have 3 salads that this person's not picky about. So 3 times 3, 3 salads with 3 soups. And then 1 more soup and salad combination, the one that the person is picky about. The fundamental counting principle can be extended to longer strings of events. For instance, if a restaurant has 4 salads, 3 soups, 11 entrees, and 3 desserts, the total number of meals that are possible, 4 times 3 times 11 times 3, 396. Another example, how many different ways can a group of 4 people stand in line? So I recommend pausing the video for just a second before seeing my solution. There's 4 different ways of picking who the first person is going to be in that line, and then regardless of who you pick, there's 3 people left that could potentially go in that second position. And then regardless of who you pick there's 2 people left for the third, and 1 person left for the fourth. So the fundamental counting principle says there are 4 times 3 times 2 times 1, or 24 possible ways of ordering these 4 people in line. This sort of calculation comes up all the time, so much that it's given its own name and its own notation. N factorial, N exclamation point, means just to add the digits starting with 1 and going up to n. So for instance, 3 factorial is 1 times 2 times 3, 6, and 10 factorial is 1 times 2 times 3, ... all the way up to 10. Factorials get very big very fast. Even just with 10 factorial, we're already well over 3.5 million. Here's another example, not identical to the last one. Again, I recommend pausing to work on this one. 12 horses enter a race. How many ways can they win, place, and show? So finish first, second, and third. There are 12 possible winners, then 11 possible second place finishers, and then 10 possible third place finishers. So overall, 12 times 11 times 10, or 1,320 possible ways that those first 3 positions could be filled. So this is another multiplication principle problem. It is reminiscent of factorials as you look at that 12 times 11 times 10. So we should try and close the loop on that connection. So more generally, suppose we have n total things and we want to pick k of them in order. We want to arrange k of them. So the way we're going to do that is just like we did with the win, place, show example. There's n ways of picking the first thing, n minus 1 of the second, n minus 2 of the third, and so on. And we keep doing that, multiplying down until we have a total of k things, the total number that we need to arrange. We denote this npk, which we read n permute k. We can write it more succinctly like this, n factorial over n minus k factorial. And if you write out those factorials, everything on the denominator has a match in the numerator. So all the things from the denominator cancel with things in the numerator, and we get left with this original formula. Here's an example. You have a collector with 53 figurines, and they want to arrange 8 of them on a display shelf. So when I say arrange them, I mean that order is going to matter here. How many ways can it be done? So pause and give it a try. This is 53 permute 8, and we can evaluate that by doing 53 factorial over 45 factorial, and there are going to be almost 36 trillion possible ways to do this, so a great number. One small warning on this: if you're doing this like on a calculator, for instance, 53 factorial may well cause an overload error, and so this is one that you probably just want to do with the multiplication that I have on the lower left, 53 times 52, etc., down to 46, which won't overload most calculators. Permutations count the number of ways in which k things can be picked in order from a collection of size n, but sometimes order doesn't matter to us, and we just need to know how many groups of that certain size are possible from a collection of size n. There are going to be fewer possibilities, and we call them combinations. Here's the formula. It's really similar to the formula for permutations. The big difference between them is that in the formula for combinations, we have that extra factor of k factorial in the denominator. So algebraically, npk is nck times k factorial. And this has a natural interpretation in terms of the multiplication rule. To get npk, the number of ways that we can arrange k things out of a collection of n, we first choose the k things, so that's n, choose k ways, and then we arrange them. So the number of ways we can arrange k things is k factorial. Again, multiplication rule, fundamental counting principle, lets us just multiply those two numbers to get npk. It's essential to keep in mind that permutations count possibilities when order matters, combinations count possibilities when order does not matter. So when you're doing word problems that have to do with counting, this is an important thing to keep in mind. One of the first things I'm always looking for is, does order matter? It's also worth bearing in mind that there are never more combinations than permutations. Combinations, you're just choosing the things. Permutations, you also have to put them in order. Another example, 3 of 12 horses in a race are randomly selected for drug testing. So the number of ways the horses can be chosen is 12 choose 3. Here order doesn't matter, unlike in the win, place, show example. 12 choose 3 is 220. Here's one for you to try on your own. How many ways can a committee of 4 people be formed from a class of 20 students? So order doesn't matter, so we're going to compute combinations. 20 choose 4 is 4,845. Related example, how many ways can a committee of 4 people be formed from a class of 20 students if the committee has to include a president, vice president, secretary, and a treasurer? So this time, order matters. We have 20 ways of picking the president, then 19 of picking the VP, 18 of the secretary, and 17 of the treasurer. This is 20 permute 4, 116,280. How many ways can a committee of 4 people be formed from a class of 20 if one person has to be designated the president? So unlike in the last example, we're not designating the VP, secretary, and treasurer. So this time we need 2 steps. We're going to apply the fundamental counting principle. First we pick the president, and of course there's 20 ways we could do that. And then we have to choose the remaining 3 members of the committee. And for those 3 people, order doesn't matter. So overall, the number of ways it can be done is 20 times 19 choose 3, 19,380.